So, to recap, a metapopulation is a population of populations. And all of those populations we refer to as subpopulations or sites or sometimes patches, and they're connected in some fashion. We see that those subpopulations will wink in and wink out over time. Some will go extinct, some will become colonized, so they're constantly winking in and winking out. The persistence of that metapopulation, if we have a species behaving as one, the persistence of that population really is something that we're concerned with, and we would focus on trying to estimate what it takes for that system to be persistent, right? So we're concerned with a stable metapopulation or one that is in some form of equilibrium. So a metapopulation that's in equilibrium is stable from one year to the next. In other words, the rate of those that are winking in and winking out kind of balance each other out. So if we can figure out that equilibrium, that gives us a great means of trying to figure out or make better decisions about the management of a species and a system. So we're going to run through the basic metapopulation model, which allows us to estimate equilibrium and to figure out ways of charting the dynamics of a metapopulation over time. So let's consider another example, one I guess that's even less glamorous to some than marmots. Let's consider gerbils, right? Mongolian gerbils. Imagine yourself again back out in the plains of Mongolia. Gerbils, like marmots, live in colonies. Colonies are at a much smaller scale, but we have multiple social groups occupying a colony, and those colonies consist of multiple burrows. And across the landscape, we have a series of colonies that are connected in some fashion through dispersal. So let's say, in building this basic metapopulation model, that we need to know some information about these colonies existing, these subpopulations existing in the landscape. So I'll introduce a new term, and that's the value F. And F is simply the fraction of occupied sites, fraction in our total metapopulation of those sites that are indeed occupied. So that value of F would range from 0 to 1. If it's 0.5, we have 50% of our sites then being occupied. If it's 0.7, we have 70% of all of our sites or subpopulations being occupied. So how does F change over time? We may be looking for a consistent F, right? One that is in equilibrium. But how does F change over time? It's really a function of the winking in and winking out. It's a balance between the gains from winking in and the losses that come from winking out. So we would express F and this notion of winking in and out the following way. We would express this as dF over dt equals I minus E. Sounds a little complicated. Basically, what this expression here means is that the change in F, the change in the fraction of occupied sites over time, is a function of immigration or colonization and extinction. So the I term here is the rate of immigration. And the E term here is also a rate. It's the rate of extinction. I minus E. If we have more immigration occurring in our system than we have extinctions now, we then have the rate of change in our metapopulation being positive. We're gaining more sites than we're actually losing. Make sense? If we now have more extinctions than we have immigration events or colonization events, we have the opposite. We now have a population, a metapopulation that is in a declining state. So it's not sustainable, let's say. In order to estimate what I is, we need to know a couple of things. So in order to build on this basic notion here of I minus E captures the state of our metapopulation, we need to define I a little bit better, and then we also need to define E a little bit better. In order to get at what I really means, we need to know a couple of things. First, we need to know the probability of a site, the probability of a site out there becoming colonized. And we're going to call that term P sub I, or PI. That's the probability of a site becoming colonized. So what factors affect PI? What factors affect PI? Well, there may be some like the area of our particular patch, habitats, the availability of food, the number of predators, competitors, and so forth. There might be some external factors as well. So if we consider our metapopulation, we might recognize that when that metapopulation is quite full, in other words, the F is quite high, the colonization rate may indeed be quite high for those unoccupied patches, right? There are lots of dispersers in the system. This is a point that we'll come back to in a little bit, but keep that in mind. So to estimate I, right, our immigration rate, we also need to know, too, now, the availability of unoccupied sites. So what is that? That's simply 1 minus F. 1 minus the fraction of sites gives us the availability, how many sites, what proportion of sites in our metapopulation are unoccupied. So 1 minus F, the immigration rate, I then, is a product of the two. Our immigration rate, or our rate of colonization, so that was our big I, is now, again, the product of the two. It's the product of the probability of colonization, so the probability that a site will become colonized, multiplied by 1 minus F. That's 1 minus the fraction of sites that are occupied. In other words, that's 1 minus those sites that are empty. Those are the only sites that can receive immigrants that can become colonized. Those sites that already are colonized can't become recolonized. So we simply multiply the two in order to get at a better definition of what our rate of colonization or immigration is across the whole metapopulation. A couple of important points. I think it's important to know that if the probability of colonization now is 0, so there's no chance of becoming colonized, then our rate of immigration or colonization is 0. Makes sense. Also, if all the sites in our metapopulation are occupied, so we have an F value of 1, we also have immigration going to 0. Sort of makes sense, right? If everything's colonized, every potential patch is filled, there's no chance that those sites can become recolonized or colonized. They're simply already occupied. So let's turn now to the extinction part of our initial metapopulation expression, I minus E. So if we look at extinction, our extinction rate for our system, we can refine that a little bit more. And we need to know a little something about the probability of sites going extinct in order to get at a better definition of what E might be. So in this case, if we've spent some time studying our system, we would estimate then a probability of extinction for a particular site. So that's the probability that a site that's out there will go extinct. If we know that value, then we multiply it by F. We multiply it by the number of sites that are out there that could become extinct. So F is the fraction of occupied sites. Those are sites existing and can become extinct. We wouldn't use 1 minus F, right? Because that represents the empty sites, those that have nothing there to begin with. There's nothing to actually go extinct. And a couple of important points to remember with this expression for E. When the probability of extinction is 0, so there's no chance a site will go extinct, then our rate of extinction becomes 0. And not only that, when we have the fraction of occupied sites also being 0, meaning there are no occupied sites, we get the same effect. We get our extinction term being 0. Should make sense. Okay, so that leads us to our basic metapopulation model. Remember, we initially said that the change in the fraction of sites in our system over time was initially I, our rate of immigration or colonization, minus E. And we've now distilled that down, we've refined it a little bit more, and we've now substituted in for I what we just covered, and that is the term probability of colonization times the number of sites that can be colonized, minus now our extinction term, which we've substituted in as the probability of extinction, times the number of sites that can actually go extinct. So this is our basic metapopulation model. What does this equation tell us? What does it really tell us? It basically states that the rate of change in F, the rate of change in the fraction of our sites, is the rate of immigration, I, right, which we've defined as PI times those sites that can be colonized. So that's 1 minus F. These are the empty sites that are ready, willing, and able to accept colonists. So PI times those available sites minus the extinction rate. And we define that again as the probability of extinction times F, or the number of sites that are actually occupied. So only those occupied sites can go extinct, right? This basic model, which we've just covered, is oftentimes referred to as the mainland island model. It's the basic metapopulation model. And one of its core assumptions is that this probability of extinction and probability of colonization, PE and PI, are constant across all of our sites. So every single subpopulation has the same PI and PE, regardless of the circumstances. So in our metapopulation of marmots, for example, if we had 90 sites out of 100 that are occupied, those 10 sites that are unoccupied stand the same chance of being colonized as a situation in which you only have, let's say, 2 sites out of 100 that are occupied. So those 98 other sites stand the same chance of being colonized as the situation in which many of the sites in the system are filled. So in order for that kind of a situation to occur, the only way that we can have this consistency, this constant PI and PE for every site, is if there's some external source that's providing immigrants, colonists, into the system. So in other words, there needs to be some mainland out there, outside of our system, that's kind of sending in colonists to our islands, which are essentially our subpopulations. So it's called the mainland island model. And in some cases, it's also referred to as the propagule rain model, meaning that, again, there's some external source that's raining in propagules into our system. So the basic mainland island model assumes that PE and PI are constant for every single site. And we'll cover shortly some variations on this model, which make some different assumptions, but this is really the basic one and a good starting point. So if we return now back to our glamorous marmots in the middle of Mongolia and our population there, one question we might ask is whether we can predict what equilibrium for our system, for our metapopulation might be. So what is equilibrium for our marmot population? That might be something that could be very valuable for us to know. We know that, of course, marmots are very endangered there, and if we can estimate what it takes for that population, that metapopulation, to be stable from one year to the next at equilibrium, that might be very valuable in terms of informing the decisions we make about management and conservation for the species. If we assume in our metapopulation that PE and PI are constant across that metapopulation, then we can apply our basic metapopulation model to estimate that equilibrium. So let's see how. So here's the basic model, which we covered before. We have here on the left side of the equation, again, the change in the fraction of sites over time in our system as being our rate of immigration minus our rate of extinction. So at equilibrium now, when the system is unchanged from year to year, time period to time period, we are, again, assuming that there's no change in our system. So in order to solve for that, in order to figure out what the fraction of occupied sites would be at an equilibrium state, we simply set the left side of our equation here, the left side, which again captures the fraction of sites over a period of time. This is our measure of change in the system, to 0. In other words, we have no change in the system. And when we do that, then we're left with the right side of the equation, and we simply solve for f, because we want to know what f will be when the system is unchanged. So this here looks a little bit different than the above, and the only difference here is that I've multiplied pi times 1 and negative f in order to get pi minus PIF. Make sense? And then this part is the same. So let's do that. Let's solve for equilibrium. Here's the same expression that we just left. And I'm now going to solve for f. In order to do that, I need to do a little bit of algebra here. And if you don't quite follow it, I would write this expression down on a piece of paper and just carry the algebra out yourself. It's really pretty straightforward. But we're going to solve for f here. And I'll start by taking these two pieces and bringing them to the other side of the equation. And that now gives us PIF plus PEF equaling PI. Easy enough? Got it so far? So I can then factor out the f on this side and then divide by PI plus PE in order to solve for f. And that then gives us this new expression here, PI divided by PI plus PE. Wow, lots of PIs and PEs. We now have f on its own, and we've given it now a little hat here. They call this f hat, meaning the fraction of occupied sites at equilibrium. And again, that means the fraction of sites that we would expect if the system is unchanged from year to year, if it's equalized. And that is the probability of colonization divided by the probability of colonization plus the probability of extinction. So we can put a few numbers in there. We can estimate, let's say, PI, I should say, to be 0.2. So that's the probability of colonization of a site. And then the probability of extinction, we would say, perhaps in this system, is 0.4. So there's a 20% chance a site will become colonized and a 40% chance that a site will become extinct. So what is that? Go ahead and enter those numbers into the equation and see what you get. So what is the result? Did you calculate it? What is f hat? It should be 0.33 or 33%. What does this mean? It simply means that the fraction of occupied sites at equilibrium, so when the metapopulation is stable from one year to the next, needs to be 33%, given our conditions. And this has, again, some good utility in terms of describing our metapopulation and some utility in terms of providing a benchmark by which we might make some decisions on managing the population. So for example, if we're monitoring our metapopulation and we see that in fact the fraction of occupied sites dips below 33%, then our metapopulation might be in decline. And so we may make some changes to ensure that we reach an equilibrium state again. So equilibrium means that the metapopulation is stable and unchanging from one year to the next. Another key point here is that we can do some simulations too. So we can estimate how equilibrium might change if our starting values were a little bit different. So for example, what if our extinction probability was 0.5 instead of 0.4? So let's say we've had a hard year and a lot of poaching of marmots that's occurred. So our extinction rate may have gone up a bit. How will that play out in terms of our equilibrium? So we can simulate that. Or we could say, what if our colonization probability was 0.1 instead of 0.2? Again, how would that play out in terms of our equilibrium? So this gives us a nice means of doing some simulations, which again might aid in our decision making about managing and conserving the species. So, to review quickly, to recap, a metapopulation is a population of populations. And those little subpopulations in there we call sites or patches, or again subpopulations, and they're linked through dispersal or immigration or emigration. So they're connected in some fashion. There is some sharing of individuals that goes on. We describe the basic metapopulation model in terms of the fraction of occupied sites, that's F, and the rates of colonization and rates of extinction of these different subpopulations. And that basic model that we've covered is referred to oftentimes as the mainland island model or the propagule rain model. I'm going to pass you over to my colleague Terry, who will build a spreadsheet, demonstrate this model, and how you can plot metapopulation dynamics over time. So Terry, on to you.